Sindhu Bushpalli. She's also part of the new FRAG team. I mean, you will see a lot of PhD students coming from the European Union ITN we are part of. Sindhu, she is at FIDAM at the University of Seville. And today she will be speaking about an analysis of unfolding failure in unidirectional and cross-ply CFRP curved laminates with some numerical and some experimental investigations. So I'm very much looking forward to your presentation and this.
Thank you so much for the introduction. Hi everyone, my name is Sindhu. I am a PhD student at FIDAM. I'm working under the supervision of Professor Graciani from University of Sevilla and Bernardo Lopez from FIDAM. So today's topic will be analysis of unfolding failure in unidirectional and 090 cross-ply CFRP curved laminates, both numerical and experimental study. So what exactly is unfolding failure? It is a sudden delamination that occurs when the curved composite laminate is subjected to bending moment, which tries to flatten the curvature, separating the plies and induces out-of-plane stresses. So this is the unfolding failure phenomenon, which occurs because of the difference in the length of the plies from inner radius to outer radius. So there are basically two types. One is a traditional unfolding, which is a classical failure mechanism that occurs in the unidirectional curved composite specimens. So what happens here is, when we apply the opening bending moment, there will be high stresses in this curved region, and when the stresses in the thickness direction reaches a maximum value, that is the interlaminar tensile strength value, then a crack is initiated in the interlaminar direction, and then it propagates to form a delamination in the interlaminar direction. So that's the traditional unfolding failure, which is governed purely by the interlaminar properties, which are the out-of-plane properties. So these properties are obtained by a 4-point bending test, generally, according to ASTM or AITM standards. So this ASTM or AITM standards are designed only for unidirectional curved composite specimens. So when we apply the same 4-point bending test specimen, which is designed for UD composite specimens, to curved composite specimens with multi-angle plies, then it is observed that the damage is initiated because of the intralaminar failure, and then it propagates further to form the interlaminar delamination under the presence of high stresses. So now, in the case of flat laminates, you have to provide additional loading to transfer this intralaminar crack to interlaminar delamination. But in our case, that is the curved composite specimens, we do not need any additional loading. That is because the curvature itself serves as a medium of high stresses. So this is a schematic representation. So here we can see that the transverse crack is perpendicular. I'm going to show the result, which is different from the perpendicular transverse crack. This is one of the experimental results which was obtained by Mr. Gonzalez during his PhD thesis. So that PhD was also done in collaboration with University of Sevilla and FIDAM. So my main objective of this project is to prove the existence of induced unfolding phenomenon, which is the initiation is because of interlaminar failure and propagation is propagates as delamination under the presence of high stresses. So before moving on to results, I want to quickly show you the 4-point bending test experimental setup. So we have here L-shaped specimen with a 90-degree opening angle. We have 2 roller supports on the top, 2 roller supports on the bottom. We apply the loading, and then we obtain this load versus displacement curve in the experimental data. So we take the maximum value, here the maximum peak load, and the corresponding displacement, and then we calculate the curved beam strength. So once we obtain the curved beam strength, then we calculate the interlaminar tensile strength. These are the analytical calculations that are employed in all our models. So now moving on to unidirectional specimens. So these unidirectional specimens, they undergo traditional unfolding failure, which is a pure interlaminar delamination. So to model the damage, interlaminar delamination, we are using the abacus cohesive elements. So with the bilinear traction separation law, we calculated the cohesive properties from using the formulas from the literature. So here we have the half of the model because of the symmetry conditions to reduce the computational time and cost. If you see very clearly, we have modified the boundary conditions to eliminate the contacts and contacts because of the roller supports. And we are applying simple rotations. We have restricted the motion in y direction here, and we have asymmetry boundary condition. Here we have 6 plies. We have introduced cohesive elements with almost 0 thickness at the interfaces. So 6 plies with 5 cohesive interfaces. So when we look at the damage, estate is a parameter which represents the resisting damage. It's not clear, I'm sorry. 0 indicates no damage, 1 is a complete damage. We can see that the delamination starts in the center in the mid-radii section and it propagates until the end of the specimen. This is a moment versus rotation curve. The moment increases linearly until a certain point, which is the peak value, and suddenly it drops, representing a very unstable propagation. So in order to capture this instability, we have used a control algorithm approach by Professor Emilio Martinez-Pineda. What we do here is we introduce 2 auxiliary nodes at the crack tip opening, and then we control the model using the crack tip opening displacement. So that's what we did for our samples with 8 plies, 16, 24 and 32 plies, and then we obtained this stable the moment versus rotation curves with the snapback behaviors for all the samples. Then we took the peak moment values and we compared them with the experiments, and I don't know why this was clear. We compared them with the experimental values and they matched perfectly well. I mean, so this, why is it, I don't know why it is clear. I'm sorry. Yeah. So this is the moment versus number of plies. So we have 4 samples.
Is the laptop, in her laptop it was okay, and I have the same problem in another room. It's just the problem of
It's a PDF in the PowerPoint file.
So sorry for the clarity. So here the solid circles that represent the moment values obtained from the numerical simulations, and the dotted lines, which is not clear here, are from the experiment. And we have 4 samples. We tested 4 samples for each thickness in our experiments. That's why we have these 4 dotted circles. We can see that they match perfectly well, which validating the usage of cohesive elements to model the interlaminar delaminations. So this is the unidirectional specimens. Before moving on to cross-ply specimens, I want to explain the stress distributions. Here we have circumferential stresses on the x-axis, and this is the thickness. Here 5 represents the inner radii and 6.4 represents the outer radii. So when we apply the opening bending moment, the inner radii is subjected to tractions and the outer is subjected to compressions. That's why we have the circumferential stresses varying from positive to negative value. And if we look at through the thickness stresses, we have this parabolic behavior with a maximum value here around 5.7 millimeter, that is the radii. That's why we have the delamination occurring at the center, at the mid-radii section for our specimen. So we checked for the stress distributions for all our samples, 8, 16, 24 and 32 plies. We have the same distribution. And we compared them with analytical results, and we can see that they match perfectly well. So this is the end of UD specimens. Now moving on to cross-ply. Cross-ply specimens, they experience induced unfolding phenomena, whereas the damage is initiated by intralaminar failure and it propagates as delamination under the presence of high stresses. So for modeling the intralaminar failure, we are using phase field fracture method for both crack initiation and propagation, and for interlaminar delaminations, we are using cohesive zone modeling. That is the one which is validated using the UD specimens. I'm not getting into details of phase field because my colleague Zeng already presented phase field, and there were a lot of presentations yesterday on phase field. So this is the phase field variable which varies from 0 to 1. 0 is no damage, 1 is complete damage. And we tested for 3 formulations, 81, 82 and phase field cohesive zone formulation. All this is implemented in a simple Emacs subroutine by Professor Emilio Martinez-Pineda. So we are using his code as a basis of our work, and we are developing further according to our problem needs. So this is the first model with 8 plies. So we have 2 90-degree plies in the bottom and 2 90-degree plies in the top. And rest of the model, we have 0-degree plies. The 90-degree plies are the weakest ones. That's why we have phase field elements in the bottom 90-degree plies where the induced unfolding occurs. And rest of the model, we have normal plane strain elements. So because of the mixture of these elements with the phase field and plane strain elements, we have imposed a 0 temperature boundary condition. Here temperature is phase field, which is damage. So we have 0 damage on the rest of the model except the 2 90-degree plies here. And we have maintained the same boundary conditions where we are applying rotations, restricting the UY motion. And this is for the 81 formulation, the first formulation. So if we look at the results, This red zone indicates the two 90-degree plies, which are the weakest plies. So the debonding starts in the bottom, it propagates to the top of the 90-degree ply, leaving behind this transverse crack. In the beginning, I mentioned the transverse crack was perpendicular, but here if we see it is not perpendicular, but it is at certain angle. That is because of the domination of shear stresses. So once this transverse crack occurs, under the impact of continuous loading, we have multiple transverse cracks that are appearing. Sorry for the clarity. Yeah, so this is very much similar to what we have in experiments where we have multiple transverse cracks. So this is the moment versus rotation graph, and we checked for the formulation for the specimens with 8 plies, 16, 24 and 32, and we obtained the same behavior where debonding happens in the 90-degree ply in the bottom. It travels to the top of the 90-degree ply, leaving behind a transverse crack and then multiple transverse cracks. So we compare, this is the moment versus rotation graph for all the samples with 8, 16, 24 and 32. We took the peak moment values here and then we compared them with the experiments. So if we look here, we have perfect correlation with experimental failure moment and the numerical failure moment. But our main focus is to determine the induced unfolding phenomena, which is a damage initiation, the intralaminar failure. So we have analytical calculations for determining the intralaminar failure for the experimental data. So we have this here, and from the numerical, we took the first phase field non-zero value as our intralaminar failure. So we have this here. Here the black color curves, they represent the experimental and numerical failure moments, that is the peak moments. And this represents the damage initiation points. The dotted lines are from the numericals model, and from this circles are from experiments, and this is from the analytical calculation. If we see here, the black curves, they match perfectly well, whereas the red ones, they do not. That is for the first formulation. That is because the only parameter that we are imposing here is the GC value. So by playing with the GC value, it is very much likely to obtain a correlation with the experimental moment, the failure moment values, but not with the initiation. Here, because the line scale is introduced as a material parameter. And if you look at the next formula, the second formulation, which is 82, here again, the failure moments, they match perfectly well, but not the intralaminar failure. We have the intralaminar failure from the numerical model is so much lower than the analytical model. That is because this 82 formulation doesn't have elastic domain, and the damage starts in the very first increment. That's why we have this very low curve for the intralaminar failure. So we then finally checked with the last formulation, that is a phase field cohesive zone formulation. And here in this formulation, we do not have line scale as a material parameter but as a numerical parameter. The only parameter that we impose in the model is the tensile strength. So by changing the values of the tensile strength, it is very much likely for us to obtain a very good correlation with the damage initiation values because it is strength driven. But if we look at the failure moment values, we have this tiny difference here with the seasonal formulation. So in conclusion, for the 81 and 82, we have very good correlation with the failure moment values, but not with the initiation. But whereas for CZM formulation, we have good correlation with the initiation, not with the final failure moment values. That is because in the phase field formulation, in this presentation, we haven't taken into account the impact of residual stresses, which is very much important for us to consider, which occurs during the manufacturing process. The residual stresses for our models is around 44 MPa, which is quite a significant value which has to be considered. So coming to conclude my talk, for the unidirectional throat specimens, we had very good correlation with numerical and experimental failure moment values, validating the usage of cohesive elements for damage modeling, that is interlaminar delaminations. And for the cross-ply specimens, as I already mentioned, the transverse crack is not perpendicular but at an angle because of the domination of interlaminar shear stresses. And for 81 and 82, we have good correlation with the moment values, not with the initiation. But for CZM, we have good correlation with the initiation, not with the moment values. That is because of residual stresses, which has to be taken into account. That is undergoing research. We have included residual stresses in the model, and we have done some preliminary tests on simple models, and it seems to be working fine. And next step is to implement on the coronary specimen. And that's it. Thank you.
cohesive zones and phase field model, which is open for discussion. Other questions?
Okay, thank you so much for the good presentation. I would like just to ask, you said that you consider that the damage with the phase field model, damage would be considered to like appear once the first non-zero phase field value, right? Why not to make it until let's say close to 1? You know, because actually phase field is developing. So if you consider the first non-zero value maybe 0.1, so actually it's not very...
It is the tiny value, but as I said, the intralaminate failure may not lead to the final failure, but it is a cause for the final failure, right? So we consider the phase field non-zero first value as our intralaminar failure in the models. And for the analytical calculations, we use a point-wise stress criterion to obtain the intralaminar failure values.
Okay. Okay. Thank you.
For the 82 model, if that's a problem with the 82 model because the first increment itself is like non-zero value. That's why we are not considering 82 in our models.
Yeah,
But we still checked for the results with all the formulations.
for 82 maybe you should wait until it becomes 1, because 82...
1 is a complete failure, which
Yeah,
we
but
cannot take
the-
into account for our intralaminar failure.
Okay. Okay.
Maybe can you comment also on the impact of the length scale parameter in that context? I mean, you said when you're almost reaching 1, then you have the failure. But can you comment on the influence of the length scale parameter? How do you choose?
Yes, length scale parameter we have. So we have this formulation for the length scale for 81 formulation. It is a material parameter which is dependent on the GC and the strength value. So we have to maintain this relation. Our strength value in our models is around 64 MPa. So we keep this constant and we play with the values of GC and then we obtain the length scale. But if we try to comply with this formula, the length scale value will be so much higher, even bigger than the model thickness itself. But according to the phase field formulation of Professor Martinez Emilio, we have to consider it as a material parameter. So, but when we try to include the residual stresses and maintain the sigma c value, we are obtaining good results.
Thank you. Yeah, are there some more questions? Yes, no. So then thanks again for the presentation.